Welcome and thank you for joining. In this lesson, we'll explore how to use the first derivative to draw the graph of a function. Now, the main purpose of using the first derivatives in drawing graphs of functions is to determine where the functions are increasing or decreasing. And we also use the first derivative to find where the maximum or the minimum point of a graph of a function occurs. Or in other words, the turning points, or as we are going to call them from now on, the critical points on the graph of a function. Now, by definition, we say that if x1 and x2 make an interval I, where x1 is on the left, x2 on the right, or in other words, x1 is less than x2, if f of x1 is also less than f of x2, then the function f of x is increasing on this interval. So, graphically speaking, we're going to say that the function is increasing when, as we walk on the graph of a function from left to right, just like when we read a book, the pen goes up. In this example, the interval x1 and x2 is an interval where the graph of a function is increasing. The corresponding values of x1, the corresponding y values of x1 are f of x1 and f of x2. And as you can see, the value of f of x1 is lower than f of x2, which means that you start with a low y value and with a higher y value. I like to remember this definition also by thinking that the direction of inequality will go in the same direction. So, similarly, we're going to say that a function is decreasing in an interval I where x1 is less than x2 if f of x1 is higher than f of x2, which means that starting from left to right side of the interval, we go from a higher to a lower point. So graphically speaking, we're going to say that the graph of a function is decreasing if, as we walk on the graph from left to right, just like when we read a book, then the pen will go down. As you can see in this interval starting from x1 ending at x2, we start at a higher value of f of x1 and go lower. So in other words, I like to remember this definition by thinking that the directions of inequalities go in opposite directions. So again, just to summarize the definitions and what we discussed, we're going to say that increasing means that when reading the graph left to right, the graph will go up. And the set of x values for which the function is increasing is called an increasing interval. Decreasing means that when reading a graph from left to right, again, just like when we read a book, the graph goes down. And the set of x values for which the function is decreasing is called a decreasing interval. Now, from now on, we will analyze the graphs of functions slightly differently by using the calculus tools or by using the first derivative and the second derivatives in the coming lessons. So we are going to say that if f prime of x is positive for every x value on some interval, then f of x is increasing on I. So referring to the graphs of the function that we drew above, we're going to say that if we draw the tangent line at any point on the interval starting from x1 to x2. And notice that the slope of the tangent is positive, which means that the derivative of the function is positive. It means that x1 to x2 will serve as an increasing interval for the function f of x. Similarly, we're going to say that if f prime x is less than 0 for every x on some interval I, that means that f of x is decreasing on I. So as you can see here, this function is decreasing, and if we were to draw a tangent at any point on the graph of this function in the interval from x1 to x2, you see that the slope of the tangent is negative. Slope negative means that the derivative of the function is negative, which means that we're going to say that if f prime is negative, then the function is decreasing. Now let's take a look at example number 1 and see how we can apply the derivative of a function to determine the intervals of increase and decrease. First, I will be highlighting the graph of the function as I go, and I'll try to highlight with different colors, the decreasing and increasing intervals. Remember that we read the graphs always left to right, just like when we read a book in English. And we're going to say that as I walk on the graph from the left end all the way down here at what we call the turning point, then the function is decreasing. So I will highlight this in blue. So I will continue my journey here. So after the turning point, then the function is increasing. And then after the next turning point, the function is decreasing again. And then after the last turning point, it is increasing. So let's read the x values for which the function is either increasing or decreasing. So we're going to take a look at the first piece that is in blue. And you see that this will start at negative infinity and will end at x equals negative 2. So we are going to say that for the x values from negative infinity, so for all these x values here, negative infinity, up to x equals negative 2, the graph of this function will be decreasing. So I will try to highlight this a little bit more gently here. So this will be a decreasing interval, starting from negative infinity, ending at negative 2. Then from negative 2 up to x equals negative 1, you notice that the graph of the function is going up. So this means that this would be an increasing interval from negative 2 to negative 1. So right here. So let's write them down as we go along. So for x values from negative infinity to negative 2, the function is decreasing. And for x values starting at negative 2, ending at negative 1, function is increasing. So continue our journey again. The next piece of the graph, the blue section of the graph, is decreasing. And this lasts, or it starts at negative 1 and it lasts until x equals 1. So in this case, we're going to say that from x equals negative 1 to x equals positive 1, the function is decreasing. So that means that negative 1 to 1 will serve as an interval of decrease. So the last section of the graph starts at 1 and it will end to infinity. And that means that the function, as you can see in here, will mark a increasing interval from x equals 1 all the way to infinity. That will be an increasing interval. So join by 1 to infinity. Now, as you can see in here, we are using round brackets around the increasing and decreasing intervals because, as you can see again, we are looking at where the values of the derivative are either positive or negative. So we're not looking at the points where the derivative is equal to 0. So next, we have to determine the points where the tangent of the function is horizontal. And as you can see in here, we can draw a horizontal tangent right here at x equals negative 2. We can draw a horizontal tangent at x equals negative 1 and a horizontal tangent at x equals positive 1. So you can see that when the tangent is horizontal, the slope is 0. Or in other words, we're going to say that the derivative will be equal to 0 at x equals negative 2, x equals negative 1, and at x equals positive 1. So we're going to say at all these x values, the derivative of the function would be equal to 0. So in the next section of the lesson, we will discuss how to find the intervals of increase and decrease algebraically. So in this example, we have a function h of x equals 2x cubed plus 3x squared minus 72x, and we need to determine the intervals where the function is increasing or decreasing. So knowing that a function is increasing when the derivative is positive, then we're going to say that increasing intervals will be wherever h prime is positive, and decreasing intervals will be wherever h prime is negative. So step number 1 would be to differentiate the function. So h prime x equals 6x to the power of 2 plus 6x minus 72. Next, we need to find the zeros of the derivative because we are trying to find the intervals where the derivative will be either positive or negative. And the zeros of any expression will separate the negative values from its positive values. So h prime x equals 0 means that 0 equals 6x squared plus 6x minus 72. Now we are solving for x. I will solve by factoring. So x squared plus x minus 72 over 6 is 12. Complete your factoring here. So x plus 4x minus 3, which means that either x plus 4 is 0, which makes x equal to negative 4, or x minus 3 is 0, which means that x must be equal to 3. So in order to study the sign of the derivative, that's our next step, we're going to use a chart. Now, obviously, this is a very simple polynomial function. We have graphed many of them, and we can determine the sign of the function just by looking at the zeros of the derivative. So we're going to, or we can determine the increasing, decreasing intervals just by looking at the zeros. But I'm going to use the chart in here because as we move on or as we analyze more complicated functions, using a chart becomes a must. And it is easier when we kind of get used to it in a easier kind of setting. So what we are going to do here is first number the number lines. So we have x equals between from negative to positive infinity, and the zeros of the derivative must be placed in order from negative 4 and 3, not to scale. So it's our choice if we would like to study the signs of each factor separately, so the sign of x plus 4 and the sign of x minus 3, or you can simply write the equation of the derivative and just use input values in here to determine the sign. So for now, I'm going to use each factor because that's what we traditionally do in more complicated examples. So we try to keep things more distinct and clear that way. So I'm going to drop the perpendiculars in here. So x equals negative 4 will be the zero of the factor x plus 4, and at x equals 3 will be the zero of the factor x minus 3. Oops, that turned out very interesting. So the sign of the first derivative will be determined based on the signs of x plus 4 and x minus 3. As you can see, these are two linears with positive leading coefficient, which means that the values of y will go from negative, hit 0, and then become positive. So that means that for the first factor, we have negative, and then after 0, it turns positive. The second factor, x minus 3, will be negative initially, and after it hits the 0, becomes positive. Now, based on the signs of each factor, we are going to determine the sign of the derivative. So remember that two minuses will make a plus. So I will indicate this one in here. So a plus and a minus will multiply to a minus, and two pluses will multiply to a plus. So the sign of the derivative will be positive for x values between negative infinity and negative 4, and from 3 to infinity. And it will be negative between negative 4 and 3. So the behavior of the function then will follow the sign of the derivative. So wherever the sign of the derivative is positive, the function will be increasing. And wherever the sign of the derivative is negative, then the function will be decreasing. So therefore, we're going to say that f of x is increasing. Let's be consistent. H of x is increasing. For x values from negative infinity, negative 4, joined by 3 to infinity. And hx is decreasing for x values from negative 4 to 3. And voila. So This is the end of example number 2. We'll continue with the rest of the examples in the next video. Thank you for learning with me, and bye for now.